All right, let's jump right in. I want to start with a pretty big idea. Something you might not believe at first, but trust me, by the end of this, I think you'll see it's true. And it's this: you're already a scientist. You know that feeling, right? When you're just stopped in your tracks, looking up at a sky full of stars, feeling kind of small, but also just full of wonder. Maybe you've asked yourself that very question. Or, maybe you've watched a flower open up and just wondered, how does it do that? That feeling, that little spark of curiosity, well, that's where everything begins. Because you see, that natural curiosity, that simple act of just wondering, it leads us straight into a world that's built on questions. I mean, just think about it for a second. We're all born explorers, right? When we were kids, we were constantly poking things, touching things, and most of all, asking why about, well, everything. It's just built into us. And that whole process, that journey of asking and poking and trying to figure things out, well, we actually have a name for it, and it's way more than just a class you take in school. We call it science. Okay, I know that definition sounds a little official, a little textbooky, but what it really means is simple. Science isn't just a big book of facts. It's a verb. It's something you do. It's a way of thinking and acting to make sense of the universe. And this is where it gets really fun. Let's just forget the idea of a sterile lab with beakers and stuff for a minute. Instead, I want you to think of science as this huge, epic adventure. Or how about this? Think of it like a giant, never-ending jigsaw puzzle. Every single discovery is a new piece you get to click into place. And the coolest part? Every piece you add just shows you more of the puzzle that's still left to solve. It never ends, and that's what makes it so amazing. So, if science is this big adventure, how do we navigate it? What's our map? Well, it turns out the tool we use is a method you're already an expert at, even if you don't know its official name. And here it is. It's called the scientific method. It's basically these 5 steps. You observe something, you ask a question about it, you make a guess, you test that guess, and then you analyze what happened. I know. Seeing it all listed out like that, it sounds kind of formal, maybe a little intimidating. But I promise you, this isn't just for scientists in lab coats. You do this all day, every day, without even thinking about it. Okay, let's use a super simple, everyday example. Picture this. You're writing, and all of a sudden, your pen just stops working. Ugh. So what do? Well, first, you observe the pen's not writing. Then you question, why did it stop? You make a quick guess, probably something like it's out of ink. So you test it, you unscrew the pen to look inside. And finally, you analyze the result. Yep, the little ink tube is totally empty. Your guess was right. See? You just did science right there. And that right there, that brings us right back to where we started. That whole thought process, solving that tiny problem, that is exactly how a scientist thinks. And it's not just about pens, obviously. It's everywhere. It's the cook in the kitchen wondering, why did my dal boil over? It's the mechanic listening for the hiss to find a leak in a tire. It's the electrician figuring out why a light bulb won't turn on. They are all using this exact same method. And this is really the main takeaway here. The exact same way of thinking that helps the scientist uncover the secrets of a distant galaxy is the same way of thinking we use to figure out what went wrong with a new recipe. The scale is totally different, but the core process, it's identical. So if the thinking is the same, then where's the lab? The answer is, it's literally everywhere. Your laboratory is right outside your window.
It's in the driest, hottest deserts.
And it's in the deepest, darkest parts of the ocean. The lab isn't a building. It's a mindset. It's a way of looking at the world wherever you are. Okay, so the lab is everywhere. The method is something you already use. So how do we lean into this? How do we become more intentional about our inner scientist? It all boils down to one thing, really. Be curious. Pay attention. Really look at the world around you. That keen observation, that's the starting line for the whole entire process. And it's not enough to just see things. You got to ask about them. Don't just notice the sky is blue. Ask why it's blue. Which brings me to this fantastic quote. To be a wise person, you must be a wise person. So that's really the only thing left to ask yourself. Your laboratory is all around you, and you've already got the tools. So what are you going to be curious about today? So here's a question for you.
What actually makes something alive? Sounds pretty simple, right? But you'd be surprised how tricky the answer can be. We're going to dig in and uncover the real rules that separate the living from, well, everything else.
I mean, think about a car for a second. It moves. It uses energy, gasoline. It even lets out exhaust fumes. It kind of checks a few of the boxes, doesn't it? But of course, we all know a car isn't alive. So right off the bat, we know there's got to be more to it than just movement and energy. Okay, now let's flip that idea on its head. Picture this. You're walking outside and you see a snail shell. It's just sitting there, perfectly still. It's not eating, it's not moving. It basically looks like a little rock. And yet, you might pause before you pick it up, right? Because what if there's a snail in there? How can something that looks so, well, dead actually be alive?
And that is the heart of the puzzle, isn't it? What we see on the surface can be totally misleading. So to really figure this out, we need a proper set of rules, a kind of definitive checklist for life.
So let's put on our detective hats. We're about to go through the 7 key signs of life. These are the big clues that every single living thing has in common. All right, first up is movement. And this one feels like a no-brainer, right? Animals walk, they fly, they swim, easy. But what about plants? They're not exactly going for a jog. And yet, they do move. Think about a flower opening up in the morning or a plant bending itself toward a sunny window. So movement is more subtle than just, getting from point A to point B. Okay, next on the list, growth. This is another big one. You're not wearing the same shoes you did when you were 5, right? That's because you grew. It's a fundamental part of being alive. Living things change. They get bigger. A car, well, it's the same size on the day it rolls off the lot as it is 20 years later. So where does all the energy for that growth even come from? For us and all living things, it's basically a 2-part deal. First, you need food, right? That's nutrition. Then you need to breathe. That's respiration, which is how you turn that food into actual usable energy. Now, a car uses fuel, for sure, but that fuel just makes it go. It doesn't help the car build new parts or get any bigger. And you know what comes with using all that energy? Waste products. And every living thing, without exception, has to get rid of that junk. We call this process excretion. It's basically life's little cleanup crew, keeping everything inside running smoothly. And yep, you guessed it, plants do this too. You ever see those little water droplets on the very tips of leaves in the morning? A lot of people think that's just dew, but it's often the plant itself actively pushing out extra water and minerals. That's excretion, plant style. Okay, here's a big one. Living things aren't just passive blobs. They react to the world. If you accidentally touch something hot, you don't sit there and think about it, do you? No! You pull your hand back instantly. The heat is the stimulus, and pulling your hand away is the response. Every living thing does this in some way. And last but not least, the one that makes it all keep going, reproduction. Living things make more of themselves. It's how life continues on, generation after generation. I mean, it's pretty obvious, but you're never going to walk into a garage and find 2 cars making a little smart car, right? All right, so we have our list now, but I bet some of you are thinking about plants. They're kind of the weird ones, right? They don't walk, they don't talk, they just sit there. So let's really put them to the test. Are they as boring and passive as they look? Well, check this out. This is a sundew plant. Looks pretty, right? Like it's covered in little dewdrops? But here's the thing. It's a hunter. The moment a bug lands on those sticky little hairs, they curl inward and trap it for food. That's movement and nutrition, all in one go. Pretty cool, huh? And what about responding to the environment? This little guy is called a touch-me-not plant, and it's amazing. Just a gentle touch, and whoop, the leaves instantly fold up. That's a super clear, super fast response to a stimulus. So yeah, plants are definitely paying attention. Okay, now that we have our full detective kit, let's go after the ultimate mystery, the seed. This is the perfect test for everything we've just learned. Think about a bean seed from a packet. It doesn't move, it's not growing, it's not eating. For all intents and purposes, it looks like a tiny little rock. Is it alive or is it non-living? How can we possibly know for sure just by looking at it? Well, we can't just look, we have to test it. And the best way is with a simple experiment. We'll take 4 pots, put some bean seeds in each, and then give each pot a different set of conditions. We're going to play around with water, air, and sunlight to see if we can coax that hidden life out.
So here's what we're going to do. Pot A gets sunlight but no water. We'll call that the desert. Pot B gets sunlight but way too much water, so the seeds are basically drowning. Pot C gets just the right amount of water, but we'll stick it in a dark closet. And Pot D gets what most of us would think is the perfect combo: good soil, water, and plenty of sun.
And the results are in. Pot A, the dry one, nothing. Pot B, the flooded one, also nothing. But look at this. Both Pot C and Pot D, the ones with the right amount of water, they both sprouted. It didn't even matter if they were in the dark or in the light.
So what does that tell us? It's huge. The seed was alive all along. It was just sleeping, dormant, waiting for the right signal. And it turns out that signal wasn't sunlight. It was the perfect mix of water and air that told it, okay, time to wake up and grow. So after all that, looking at cars, plants, and now this amazing little seed, we're finally ready to put it all together. We can build a real, solid definition of what it means to be alive. Here it is, the whole shebang. For something to be alive, it has to check all these boxes. It moves, it grows, it uses energy, it gets rid of waste, it responds to things, and it can reproduce. But, and this is the big lesson from our seed experiment, it doesn't have to be doing all of them right this second. It just has to have the potential to do them. And this helps us understand a really important difference. A rock is non-living because it never had these abilities in the first place. But a tree that used to grow and respond but can't anymore, even if you give it water and sun, that tree is considered dead. It's lost the potential that it once had. So it turns out being alive isn't always about action. Sometimes it's about potential. It's this incredible built-in ability just waiting for the right moment, the right conditions to spring into action. And that really makes you look at the world differently, doesn't it? It makes you wonder, what else out there just looks like a rock, but is actually just waiting for its chance to come to life? You know, every single day, we make a ton of choices about what to put on our plates. But how often do we stop and think about what that food really is, or what it truly means to eat mindfully? Today, we're going to dig into the science behind our meals and find out. Okay, so there's this ancient Sanskrit saying that asks a question, not just once, but 3 times. Who is healthy? The repetition tells you something, right? It suggests the answer is a little deeper than you might think. And the answer from that same ancient wisdom? Well, it's actually pretty straightforward. A healthy person is someone who eats wholesome food, doesn't overdo it, and eats what's right for the season and the place they live. This idea, right here, is the heart of mindful eating. So, to really get a handle on mindful eating, we've got to go back to basics. Like the most fundamental question of all. Why do we even eat in the first place? This idea is beautifully summed up in another powerful Sanskrit phrase, Anena Jatani Jivanti. It basically means food gives life. Simple, right? But so profound. Food is literally the fuel and the building material for our very existence. Okay, so food is universal, we all need it. But then, why are our diets so incredibly different all over the world? Well, it turns out the answer is basically written on the map. Here's the thing. What our ancestors ate has always been tied to where they lived. The soil right under their feet and the climate all around them, that's what decides what can grow. And whatever grows, well, that's what ends up shaping the local food culture. And you can see this so clearly when you look at a few examples. Let's take a little trip, shall we? Head to Punjab, where maize and wheat grow like crazy. And what do you get? Classics like makki di roti. Now, let's go south to Karnataka, where rice and coconut are everywhere. And boom, you've got idli and dosa. Then, way over in Manipur, rice and bamboo are staples, forming the base of dishes like eromba. Our plates are literally a reflection of our local geography. But you know, it's not just what we're eating that's changed over time, it's also how we cook it. The journey of our kitchen has been a pretty wild ride, from stone and fire to steel and electricity. So, take a look at this. On one side, you've got the traditional chulha, a wood-fired stove that was the absolute heart of the kitchen for generations. And on the other, the modern gas stove we all know. This isn't just a small change, it's a total revolution in how quickly and easily we can cook. And this leap in technology isn't just about heat.
Look at this comparison. The silbata, a manual stone grinder, that's a serious workout. Compare that to the flick of a switch on an electric grinder. Technology has completely changed the physical effort that goes into making a meal. Okay, so whether our food is slow cooked over a fire or zapped in a blender, what's actually inside it that gives us life? Let's get into the nitty-gritty, the essential nutrients that make it all happen. All right, first up, carbohydrates. The easiest way to think about these, they're the premium gasoline for your body's engine. They give us the immediate energy we need for, well, for everything. Thinking, moving, you name it. And you find them everywhere. In some of our favorite foods, right? Staple grains like wheat and rice, hearty veggies like potatoes, and of course sweet, delicious fruits like bananas and mangoes. So carbs are part of a team called energy-giving foods, and their partner is fats. But they have totally different jobs. Carbs give you that quick, instant burst of energy. Think of a runner sipping on glucose water. Fats, they're more like the battery reserve, a source of stored energy to keep you going for the long haul. Okay, next up, we've got proteins. Now, if carbs and fats are the fuel, then proteins, they're the construction crew. They're the ones actually building and repairing everything in our bodies, from our muscles to our cells. That's exactly why we call them bodybuilding foods. So we've got fuel and we've got building materials, but what about a defense system? That's where vitamins and minerals come into play. They're like our body's unseen protectors, fighting off trouble. So let's play detective for a minute and jump back in time. For centuries, sailors on these super long voyages faced this absolutely terrifying illness. Their gums would bleed, and even tiny cuts just wouldn't heal. What was going on? The culprit? A disease called scurvy, and the cause was shockingly simple: a lack of vitamin C. Once they figured that out, the solution was just as simple: pack citrus fruits like lemons and oranges for the trip. It's one of history's great nutritional detective stories, for sure. Okay, here's another puzzle for you, but this time we're heading to the mountains. In places like the Himalayas, it was really common to see people with this very specific swelling on their neck. What on earth was going on there? Well, that condition is called goiter, and it's caused by a lack of the mineral iodine, which just wasn't present in the local soil or water. The public health solution to this was honestly brilliant. They just added a tiny bit of iodine to table salt, a simple, small change that solved a massive, widespread problem. So, we've gone on quite a journey, right? We've looked at where our food comes from, how we cook it, what it's made of. Now, let's put all those pieces together and figure out what a truly mindful diet actually looks like. But wait, there's one more crucial player we can't forget: dietary fiber, or what some people call roughage. Now, this stuff isn't technically a nutrient, but it is absolutely essential. Think of it as the cleanup crew for your digestive system, helping to get rid of all the undigested stuff and keep things moving. So here's the bottom line. A healthy, mindful diet isn't about focusing on just one thing. It's all about balance. You need those energy givers, your carbs and fats. You need the bodybuilders, your proteins. And you absolutely need those protective nutrients, the vitamins and minerals. And that really brings us full circle, because mindful eating isn't just about memorizing nutrients. It's about understanding the whole story of your food, where it came from, how it was made, and what it does for you. So the question I want to leave you with is this. Knowing what you know now, how can you make your very next meal a more mindful one?
Today we're diving into magnets. You know, that invisible force that somehow guides sailors and keeps your life organized. But how does this thing actually work?
Okay, I want you to picture this. You're a sailor, hundreds of years ago. It's just you, the creaking of your ship, and this vast, endless ocean. Your only guide? The stars. That's it. Your life, your crew, everything depends on you seeing those stars at night. And then, a storm hits. The sky just goes dark. The stars are gone, the sun is gone, all you can see is gray, everywhere. You are completely and utterly lost. So, what do? This wasn't just a story, This was a very real life-or-death problem for sailors. Now let's fast forward. It turns out that same life-or-death problem became a major roadblock for a storyteller living today. This is Reshma. She's writing this amazing story about ancient traders, but she hits a wall. Her characters get caught in a storm, no stars in sight, and she realized she had no idea how they could possibly find their way home. She was just as stuck as they were.
So, her search for an answer for her characters led her to this incredible piece of ancient tech, a kind of secret weapon for navigation that worked even when the sky was totally blacked out.
She learned that for centuries, travelers had a special tool that didn't need the sky at all. And what she found was the magnetic compass, a simple device with a needle that spins around but always stops pointing in the exact same direction. For Resma's sailors, this little gadget wasn't just a tool. It was their ticket to survival. So how does it work? Is it magic? Nope. The needle itself is just a tiny magnet, and it's lining itself up with a much bigger magnet, planet Earth. Yeah, our entire planet has a magnetic field, and the compass needle just snaps into line with it, pointing north-south. Okay, to really get to compass, we've got to get magnets. And the whole secret to their power is found right at the ends.
So if you've got a regular bar magnet, where do you think the force is most concentrated? Is it spread out all over, or is it stronger in certain spots?
Well, we can actually see the answer. If you sprinkle tiny iron filings over a magnet, they don't just stick evenly. They cluster like crazy at the two ends. That shows us that the magnetic force is strongest right at these points, and we call them the poles.
Every single magnet has two of these poles, a north pole and a south pole. This is where all the action happens.
And here's a wild fact, like a fundamental rule of the universe. You can't have one without the other. If you snap a magnet in half, you don't get a separate north pole and a separate south pole. You just get two new, smaller magnets, each with its own north and south.
So now that we get the whole poles thing, let's talk about the super simple rules that explain how all magnets interact.
The rules are incredibly simple. Opposites attract. A north pole will always try to pull the south pole closer, but poles that are alike, they repel. If you bring two north poles together, they'll push each other apart. Same thing for two south poles. That's it. Attraction and repulsion.
But here's a really cool insight. A magnet can attract other metals, like iron, but it will only repel another magnet. That pushing force is totally unique. So if you ever want to know if something is a true magnet, don't check if it attracts. Check if it repels. That's the real proof.
So this invisible force, with its simple rules, isn't just for sailors lost at sea. It's all around us, in things we use every single day.
I mean, the first place you'll probably think of is your fridge. Every one of those magnets holding up a photo or a grocery list is a perfect little example of that simple rule of attraction.
Or what about that satisfying snap when a pencil case closes? That little click isn't a mechanical latch. It's just the invisible force of a tiny magnet pulling that lid shut. It's in our tech, too. The clasp on your phone or tablet cover, the one that keeps it shut and maybe even puts the screen to sleep? Yep, that's a magnet, working on the very same principle that guides a compass. So let's just trace our steps real quick. We started with a sailor's huge problem and found the answer in the magnetic compass. We figured out its secret power comes from its north and south poles. And then we saw how two basic rules, opposites attract, likes repel, are behind everything from global navigation to the case on your phone.
We've just peeled back the curtain on one of nature's biggest invisible forces. It kind of makes you wonder, doesn't it? Now that you can see the rules of magnetism playing out everywhere, what other unseen forces might be quietly shaping your world, hiding in plain sight? You know, have you ever really looked at a ruler? I mean, yeah, it draws straight lines, but it's so much more than that. It's kind of like a time machine. Seriously, it's the answer to this super old, really fundamental human problem. How do we all agree on what this long actually means? Let's dig in and find out. So, it all kicks off with something super relatable. Meet Deepa. She just needs a new school uniform. We've all been there, right? But what seems like a simple task is actually going to pull her and us right into the middle of a puzzle that people have been trying to solve for, well, centuries.
And that whole puzzle? It really just boils down to one simple question. When you hold up your hands and say, I need it to be about this long, what does that actually mean? I mean, to someone else, how do they know what this long is?
Okay, so on her shopping trip, Deepa sees this whole world of different ways to measure things. First, the shopkeeper, he's using this stiff metal rod to measure the cloth. Then the tailor uses a flexible tape measure to get her body measurements. And then get this, her mom chimes in with his ancient method, telling the tailor to add Shar Ungala, which is basically the width of 4 fingers. So you've got 3 different tasks and 3 totally different ways of measuring. And this, right here, illustrates a really key point. The tool has to fit the job.
You see that rigid rod? It's perfect for a flat piece of cloth. You get a nice, straight, consistent length. But trying to measure around Deepa's arm with that? No way. For that, you absolutely need something flexible, like a tape measure. Each one is the right tool for its specific purpose.
Okay, but that brings us right back to the main problem, doesn't it? We've got rods, tapes, even fingers being used as measuring tools. How on earth can we be sure that my 4 fingers is the same as your 4 fingers, or that one person's meter is the same as another's? How do we get on the same page and create a shared understanding? So, to get to the bottom of all this confusion, Deepa and her friends decide to run a little experiment back in their classroom. And what they find out, well, it perfectly shows just how tricky this whole measurement thing can be. So here's the plan. They're going to measure the length of their classroom table, and for their tool, they pick the most convenient thing they have, their own hands. You know, a handspan, that distance from your thumb tip to your pinky tip. Seems pretty straightforward, right?
And here are the results. Whoa, look at this. Anish gets a bit more than 13. Padma gets exactly 13. Tasneem gets a little less than 13. Deepa's is somewhere between 13 and 14, and Hardeep gets a full 14. Wait a minute. They're all measuring the exact same table. How are they all getting different answers? What is going on here?
This right here, this is the heart of the puzzle. The table didn't change, so why did the numbers? What's the hidden piece of the puzzle here that's messing everything up?
Well, the answer leads them and us to this huge aha moment. See, the solution isn't about finding a better tool. It's about a better idea. And that idea is called a standard.
Here it is, the big realization. The problem wasn't the table, it was their hands. Of course, Anish, Padma, Deepa, and Hardeep, they all have different sized hands. So their tools were all different sizes. They weren't consistent at all.
And this brings us to a really core concept. Think about it. Every single measurement has 2 parts. You've got the number, right, like 13, but 13 what? Apples? Cars? The number is totally meaningless without the second part, the unit. The unit, whether it's handspans or centimeters, is what gives the number its meaning. So when you use something like body parts as your unit, what do you get? Well, you get chaos. It's totally variable, it's inconsistent, and it's just plain confusing. But a standard unit? That's the complete opposite. It's fixed, it's universal, and it's crystal clear for everybody, everywhere.
And this need, this absolute necessity for a clear, universal system, that's what led us to create what's basically a global language for measurement.
Yeah. To put an end to all this confusion once and for all, countries from all over the world actually came together. It was this massive act of global teamwork. And they created and agreed on a single system, the International System of Units, or, as you probably know it, SI units.
Now, for length, the standard SI unit they all agreed on is the meter. And you should really think of the meter as more than just a distance. It's like a word in a universal language. When a scientist in Japan says 1 meter, a builder in Brazil knows exactly what she means. No confusion. And the best part? The beauty of this whole system is how simple it is. Everything is based on tens, hundreds, and thousands. It just makes sense. 1 kilometer is 1,000 meters. 1 meter is 100 centimeters. 1 centimeter is 10 millimeters. It's so logical, so predictable, it's just easy to work with.
But, and there's always a but, isn't there? As the friends are about to learn, having this awesome system is only half the battle. You also have to know how to use it the right way. I mean, think about it. If Deepa and Anish both use the same ruler to measure the same thing and still get different answers, then we're right back at square one, aren't we? So technique is absolutely everything.
So how do you do it right? It's actually just 3 simple steps. First, place your ruler or scale flat, right up against the object. Second, look straight down at the mark. Don't look from an angle, because that can give you a wrong reading. It's called parallax error. And third, what if the 0 end of your ruler is all busted up? Easy. Don't guess. Just start at the 1 centimeter mark instead, and then remember to subtract that 1 centimeter from your final number.
Here's a perfect example of what I'm talking about. See how the measurement ends at 10.4 centimeters? But we started at the 1 centimeter mark. So we just do a little math. 10.4 minus 1.0 gives us the real length, 9.4 centimeters. It's simple, it's accurate, and anyone can do it and get the same result.
And this is why it all matters so much. Having standard units and using them the right way isn't just for a classroom experiment.
It's the invisible foundation for, well, everything. It's how we design cars, build massive bridges, and even send rockets to space. It's what lets all of us work together to build things together on a truly global scale.
But hey, just when the friends think they finally got this measurement thing all figured out, a new puzzle pops up. Anisha's family is decorating their house with these awesome, curvy string lights. And it gets them thinking, how in the world do you measure a curve with a straight ruler?
And that's where we're going to leave it for now. So we figured out how a ruler conquered the straight line. But our world, it's filled with curves and circles and all sorts of complex shapes. So the next big question is, how do we take everything we've learned and apply it to a world that isn't always a straight line? Now that is the next great puzzle in this amazing story of measurement.
All right, let's jump right in. Have you ever just stopped and thought about the stuff that makes up, well, everything around us? Today, we're going to dive into the world of materials. I mean, just look around you right now. Your phone, the chair you're sitting in, that cup on your desk. Our world is literally packed with objects, and every single one was designed to do a very specific job. But here's the real question, isn't it? It seems kind of obvious, but why? Why isn't your notebook made of metal or your house key made out of paper? The answer is actually way more fascinating than you might think. So to get to the bottom of that, we first need to get one simple definition straight. What even is a material? Well, it's just the basic stuff that an object is made of. You know, like wood, glass, plastic, clay. You get the picture. And it's super helpful to think of it this way. You have the object, the thing itself, and then you have the material it's made from. A spoon is the object, metal is the material. A book is the object, paper is the material. Simple, right? You see the difference. Okay, but think about it. There are millions of different materials and objects out there. How on earth do we even begin to make sense of all of it? Well, we do what humans do best. We sort things into groups. Scientists have a fancier name for it, of course, classification. And that's our starting point. All right, so we get what materials are, but that just leads us to the next big question. How do we pick the right one? What's the secret to matching the stuff to the job it needs to do? Well, this picture pretty much says it all, doesn't it? This is what happens when you get it wrong. Trying to hold water in a cloth bag? Yeah, that's not going to work. It fails at the one thing it's supposed to do. And believe it or not, that very simple failure tells us everything we need to know. The entire reason that cloth bag is a disaster and, say, a plastic cup works perfectly, it all comes down to one single crucial word: properties. That's it. That's the key to understanding why everything is made the way it is. So here is the golden rule, the main idea of this whole thing. The purpose of the object is what determines the properties its material has to have. It's really that simple. You just match the material's special features to what the object needs to do. Think of it like a two-step checklist. First, what's this thing for? A tumbler needs to hold water. Okay. Second, what kind of material has the right property for that? You need something that's waterproof. So plastic, glass, maybe metal, they all work. Cloth? Not so much. Let's take a really simple property, hardness. You've got materials like stone or iron that are super hard, right? They're tough to squish or scratch. And then you have stuff like an eraser or a sponge, which is obviously soft. I mean, you'd never try to build a hammer out of a sponge, would you? The properties just don't line up with the purpose. Or how about another one, luster? That's just a fancy word for how shiny something is. Metals like iron and gold have a ton of it. Wood and paper, not so much. Now, sometimes that's just about making something look nice, but sometimes that shininess has a really practical job to do. And get this. This way of thinking, of matching properties to a purpose, it isn't new at all. This is not some high-tech, modern idea. It is ancient. Humans have been masters at this for thousands and thousands of years. Check this out. There's an ancient Sanskrit text, the Raso-Retna Samochaya, and it lays out instructions for making a crucible. That's a special pot for melting things at high temperatures. And what does it say to use? Clay and iron. And why those two? Because they both share one critical property. They don't fall apart under extreme heat. And you can see this ancient wisdom in action when you look at something like the history of pottery. For thousands of years, people were basically scientists in their own right. They were experimenting with clay, figuring out its properties, and perfecting their techniques to make pots that were stronger and just plain better.
And this is what they came up with. These incredible terracotta pots, they're not just gorgeous to look at, they are marvels of engineering. The material, baked clay, was chosen very deliberately. Why? Because it was durable, it could hold food and water without leaking, and you could shape it into pretty much anything you needed.
So think about it, from an ancient potter choosing just the right kind of clay for a water jug, all the way to a modern engineer picking a special metal alloy for a spaceship, the basic idea, the core principle, has not changed one bit.
So, if you remember one thing from all this, let it be this simple phrase: the right material for the right purpose, based on its properties. That's the secret formula behind pretty much every single thing we use. So now, it's your turn. Seriously, look at the object closest to you right now. What was it made to do? And what is it about its material? What are its properties that make it so perfect at its job? Once you start asking that question, I promise you'll start seeing the world in a whole new way.
Hot, colds. We use these words every single day, and we trust our hands to tell us what's what. But what if I told you your senses can lie? That the very same water can feel both hot and cold at the exact same time. Today we're diving into the strange world of how we perceive temperature and the amazing tools we invented to finally tell us the truth.
So to kick things off, let's start with a really simple experiment, one you can even try at home, to put our own senses to the test. And this really gets to the heart of the matter. Can we always, 100% of the time, trust our sense of touch to be an accurate thermometer? Well, let's find out. Okay, check out this setup. It's pretty simple. Imagine you have 3 bowls. The one on the left has warm water, the one on the right has ice-cold water, and the one in the middle? Just plain old room temperature tap water. Now you put one hand in the warm bowl and the other in the cold one, and you leave them there for a minute or two. Then you take both hands out and plunge them into that middle bowl at the same time. What do you think is going to happen?
This is where your brain does a little flip. The hand that was in the warm water will feel that the tap water is actually cold. But the hand that was in the ice water, it will feel that the exact same tap water is warm. This is just a brilliant, simple way to show that our sense of touch is totally relative. It isn't measuring the actual temperature, it's just measuring the change in temperature. And that leads to a really crucial point, captured perfectly in this quote. If our own senses can be fooled this easily, relying on them for something important, like, say, checking if someone has a fever, is just not a good idea. We absolutely need a better, more objective way to measure things.
So if we can't trust our hands, what can we trust? Well, this is where science steps in with a really elegant solution, the whole concept of temperature. And that solution is temperature. See, unlike our own feelings of hot or cold, temperature is a reliable, objective measurement. It gives us a real number we can actually trust, and it tells us exactly how hot one thing is compared to another. No guesswork involved. And the tool we use to get this super reliable measurement is, of course, the thermometer. It's a device designed to do the one thing our hands just can't: give us an accurate, unbiased reading. But you know, not all thermometers are created equal. So let's take a closer look at the different kinds of tools we've come up with for taking temperature. Generally speaking, you're going to come across 2 main types. Over on the left, you've got your clinical thermometers. These are specialists, designed for one very specific job: measuring human body temperature. Then on the right, you have laboratory thermometers. These are the all-rounders, used for all sorts of scientific work, from chemistry experiments to checking the weather. This slide really shows the evolution of that clinical thermometer. A lot of us probably remember seeing those old mercury thermometers on the left. But here's the thing, mercury is actually pretty toxic. If one of those broke, it was a real problem. That's why they've pretty much been completely replaced by the much safer and, frankly, easier to read digital thermometers you see on the right. And the tech just keeps getting better. I mean, during the COVID-19 pandemic, we all got very familiar with these non-contact infrared thermometers, right? They're fantastic because they can measure temperature from a distance, which is obviously a huge plus for public health and stopping the spread of germs. Okay, so let's get practical. You've got your digital clinical thermometer. How do you actually use it correctly to measure your own body temperature? All right, the process is simple, but it's really important to get it right. First things first, always wash the tip. Then you hit the button to turn it on or reset it. Place that tip right under your tongue,
close your mouth, and just hang out until you hear that little beep. Then you can pull it out and read the display, and of course, always clean it again before you put it away. It's that simple.
And hey, just a few quick but crucial safety points to remember. It never hurts to give the instruction manual a quick read. Definitely wash the tip before and after every single use. When you're cleaning it, be careful not to get the digital display part wet, and try to hold it by the body, not by the sensitive metal tip.
So you follow all those steps correctly, and chances are you're going to see a number that's pretty close to this one, 37.0 degrees Celsius. It's pretty famous, right? The normal human body temperature?
But hold on a second. We've just been talking about how science is all about precision. So is it really true that every single healthy person on the entire planet has a temperature of exactly 37.0 degrees?
And here's the key takeaway. That 37.0 degrees Celsius, it's just an average. It was calculated from a huge number of healthy people. Your personal normal might actually be a little bit higher or lower. In fact, your temperature naturally changes throughout the day, and it can depend on your age, what you're doing, all sorts of things.
Okay, let's zoom out a little bit now. We've talked about measuring the temperature, but what about the units we use to describe it? Let's take a quick look at the different scales.
So this table breaks down the three main scales you'll hear about. You've got Celsius, which is used in most of the world. Then there's Fahrenheit, which you'll still see mainly in the United States. And finally, there's Kelvin, which is the standard for most scientific work. And as you can see, our average normal temperature of 37 degrees Celsius is the exact same thing as 98.6 degrees Fahrenheit. This brings up a really good practical question about using the right tool for the right job. So you've got your clinical thermometer. What do you think? Could you use it to check the temperature of a pot of boiling water on the stove? The answer is a big, definite no. And this is a great example of specialization. A clinical thermometer is built for a very narrow, specific range of temperatures, basically the range a human body can be, which is roughly 35 to 42 degrees Celsius. Boiling water is way, way hotter than that and would almost certainly break the thermometer. So we've gone on this whole journey, right? From our easily fooled hands to the precise, reliable measurements of science. We've seen how different tools are designed for very specific jobs, and that even a simple number, like normal temperature, has way more to it than you might think. And that leaves us with one final question to ponder. For almost all of human history, we didn't have these incredible devices. So how on earth did our ancestors detect something as critical as a fever before the thermometer was even invented? That's definitely something to think about.
You know, we see water every single day. But have you ever stopped to think about its secret life? I mean, from a solid block of ice to a totally invisible gas, it's on this constant journey of transformation. So today, let's follow that journey and uncover the simple yet kind of brilliant science behind it all.
So, let me introduce you to our guides for this little adventure, Avi and Theref. And like all the best scientists you see, their curiosity about the everyday world is what really kicks off our entire investigation. It all starts with a simple observation on a hot day.
And here's the question that sparks a whole debate. Is an ice cube the same thing as a glass of water? It sounds super simple, right? But is the solid ice in your drink fundamentally the same stuff as the liquid it's floating in? Let's break it down.
And that brings us to our very first mystery, the great ice cube debate.
Okay, so you can see where Theref is coming from, right? His argument makes a lot of sense. You can hold ice. It's solid. But water, that's a liquid. It just slips right through your fingers. They seem totally different. Avi, though, is convinced they're the same thing. So who's right?
Well, the proof is actually an experiment you've probably done yourself, maybe without even realizing it. Just leave an ice cube out in a cup, and you'll see its transformation firsthand. It doesn't just vanish, it melts, turning right back into liquid water. And this is our first huge clue. And that simple observation cracks the whole thing wide open. It introduces us to this core idea of states of matter. See, ice and water aren't different substances at all. They're both the exact same substance, H2O, just in different physical forms. One's a solid, the other's a liquid. And just like that, mystery number one is solved. Okay, so we solved one mystery. But you know how it is. As soon as you answer one question, another one just pops right up. Our investigation now leads us to the very strange case of the disappearing water.
So picture this. It just rained, and Avi and Thira are looking at puddles all over the playground. But after a little while, they're gone. So where does all that water go?
Does it just poof, vanish into thin air?
Now, your first thought is probably, well, the ground just soaked it up, right? Fair enough. But what about a hard surface, like a steel plate? To test this, our young scientists put a spoonful of water right onto a surface it definitely can't seep into.
And sure enough, just like the puddle, after a little bit, the water's gone. It obviously didn't leak through the plate, so what in the world is going on here? This just deepens the mystery and tells us there's some other force at play.
The answer, it turns out, is this really cool process called evaporation. Basically, with a little energy from heat, the water molecules get so excited they literally escape from the surface of the liquid. They don't vanish, they just transform into an invisible gas called water vapor and mix right into the air around us.
And this is one of those things where once you know what to look for, you start seeing it everywhere. It's why your wet clothes get dry on the clothesline, why a mopped floor doesn't stay wet, and yeah, even why hand sanitizer seems to just disappear as you rub your hands together. That's all evaporation.
All right, so water can be a solid, a liquid, and an invisible gas. But its journey isn't over yet. There's one more twist, and it brings us to our final puzzle for today, the mystery of the sweating glass. You have definitely seen this. You pour a nice cold drink, and within minutes, the outside of the glass is covered in tiny little water droplets, almost like the glass itself is sweating. But where is all this water coming from? But seriously, stop and think about that for a second. The liquid water is safely inside the glass. So how in the world does it suddenly show up on the outside?
So Avi's first hypothesis is pretty logical. Maybe the water's leaking through tiny invisible holes in the glass. But then Thirov points out a major flaw in that theory. The water level inside the glass hasn't gone down at all. So that can't be it.
And this leads to a pretty wild conclusion. The water isn't coming from inside the glass, it's coming from the air around it. Yeah, remember that invisible water vapor we were just talking about from evaporation? Well, it's in the air all around us all the time.
What we're seeing here is a process called condensation, and get this, it's basically evaporation in reverse. When that warm air, full of water vapor, hits a cold surface like our glass, it cools down really fast. This forces the water vapor to change its state back into liquid water, and bam, that's where those droplets come from.
So, let's step back for a second. We have melting, evaporation, and condensation. When you put all these pieces of the puzzle together, you get something bigger. You don't just get three separate things. You get a single, amazing system. Water's constant, never-ending journey.
It's this incredible, continuous loop. You start with solid ice, right? That melts into liquid water. Heat turns that liquid into an invisible gas. That's evaporation. Then, as that gas cools, it condenses back into a liquid, forming clouds. And finally, if it gets cold enough, that liquid freezes or falls as rain, and the whole cycle just starts all over again. And the coolest part? This isn't just some diagram in a textbook. This cycle is happening all around you right now, every single day. The puddle on the street, the clouds up in the sky, the dew on the grass in the morning, it's all part of the same incredible journey. You know, this idea isn't new at all. In fact, there's this piece of ancient wisdom from the Thirukkural, a classic Tamil text, that just nails it. It says, if it does not rain well, even the mighty ocean will be drained.
Just think about what that means for a second. It's saying that even the massive, mighty ocean depends on this cycle. It needs the rain, which comes from condensation, to replace all the water it loses to evaporation. It just perfectly shows how this cycle is literally the engine that keeps our whole planet going. So I'll leave you with this little challenge. Now that you know the secrets of water's journey, where are you going to spot this cycle in action today? Maybe it's the steam from a boiling kettle, the fog on a cold morning. Once you start looking for it, you'll realize it's happening absolutely everywhere.
Have you ever really stopped to think about the journey your food takes before it lands in your kitchen? It's this incredible story of science, of ancient tradition, and honestly, some really clever physics. So let's follow that journey, right from the field to our plate. You know, a scene like this looks so peaceful, but it's actually the final, crucial step in a super long process of purification. Before this very moment, that clean grain you see was all mixed up with dirt, stones, stalks, husks, basically everything it grew with out in the field. So that's the big question, right? The main challenge is that pretty much everything we harvest is a mixture. The delicious, edible parts are all tangled up with stuff we just can't eat.
And over centuries, humanity has developed this amazing toolkit of techniques to separate the good from the unwanted.
Okay, let's start with the most intuitive method of all, one that relies on nothing more than our own two hands and our eyes.
I mean, this is such a universal thing, isn't it? Little Molly here picking a spicy peppercorn out of his food, he's using the exact same principle as a farmer who's pulling a small stone out of a big pile of rice. Our eyes spot the difference, and our hands just do the work.
And that's hand-picking. It works perfectly when the things you don't want are easy to see, and there aren't a ton of them. The beauty of it is in its simplicity. It's all based on those basic visible differences: size, color, and shape. But what happens when the problem is much, much bigger than that? Let's move from the quiet courtyard out to the fields, where the real heavy lifting begins.
So, after the harvest, every single tiny grain is still attached to its stalk. You can't possibly handpick millions of them one by one. The very first step is to free them, and that requires some force.
This process is called threshing, and whether it's done by hand like this, by having animals walk all over the stalks, or by a giant machine, the goal is exactly the same: knock those grains loose from the plant that grew them.
And you can really see the evolution of this technique, side by side. On the left, you've got the traditional, really physically demanding method. And then on the right, a modern machine that not only threshes the grain, but can often do the next step in the process too.
Okay, so you've freed the grain from the stalk. Great. But now you've got a whole new mixture to deal with. Heavy, valuable grains mixed in with all this light, papery husk and chaff. Handpicking is still a no-go. So what's the solution?
Well, the answer is absolutely ingenious, and it uses a force of nature that's literally all around us: the wind. This next method is all about separating things based on their weight. Let's try a quick thought experiment. Picture this: you've just roasted some peanuts, and you're rubbing the skins off. Now you've got this mix of heavy nuts and super light, flaky skins all jumbled together. How would you separate them without picking them out one by one? You'd probably just blow on them, right? The light skins would fly away, leaving the heavy nuts behind.
Well, farmers apply that exact same principle, just on a much, much bigger scale. And for centuries, their key tool has been this simple but incredibly effective device: the winnowing tray, sometimes called a soup.
The technique is just so simple and elegant. A farmer stands up, maybe on a stool or a platform, and lets the mixture fall from the tray. The heavy grain drops straight down into a nice, clean pile, while the wind just carries that light, useless husk away. It's pure physics in action.
And this beautiful process is called winnowing. It's an absolutely elegant solution that relies completely on the difference in weight between the grain we want and the chaff we don't.
You know, this method is so fundamental. It's even become this powerful metaphor in philosophy. The poet Kabir used it to describe wisdom, the act of separating what's valuable and true from what's trivial and false, and just letting all the bad stuff blow away.
So we've gone from the stalk to a clean pile of grain. Awesome. Now let's bring it into the kitchen for the final stage of purification, where the differences we're looking for are way more subtle.
So when you grind grain into flour, you get yet another mixture. You have the fine flour particles you want, but you also have slightly larger, coarser bits of bran or other tiny impurities. So how do you separate things that are almost the same size?
You use a sieve. This simple tool works just like a filter. The holes in the mesh are just the right size to let all that fine flour fall through, while catching the bigger pieces of bran on top.
And that's our final key method: sieving. It's the go-to technique anytime you need to separate solids based purely on the size of their particles. You see it at home in the kitchen, and you see it on a massive scale at construction sites, separating sand from pebbles.
So there you have it. This is the separation toolkit, perfected over thousands of years. You've got hand-picking, which uses sight, threshing, which uses force, winnowing, which uses weight, and sieving, which uses size. 4 simple principles, each one tackling a different kind of mixture.
From the field all the way to our flour, these ancient methods make sure the food on our plate is pure. It really makes you wonder, doesn't it? What other incredible science is hiding in plain sight, just waiting for us to see it?
Okay, just for a moment, I want you to listen. Think about the sound of birds chirping. You've probably heard it 1,000 times, right? But have you ever stopped to really listen? Have you ever noticed just how many different kinds of chirps there are? Believe it or not, that one simple question is the key to everything we're about to get into.
So, picture this, a group of students out on a nature walk with their notebooks. They probably think they're just out for a nice stroll, but what they're really about to discover is the huge difference between just looking at the world and truly seeing it. Which brings us to the big question, right? How do we make sense of it all? I mean, if a single sound can hold so many different voices, where do you even begin to understand the incredible, mind-boggling variety of nature? And this student's comment, right here, it's perfect. It captures that exact aha moment. Suddenly, a common sound becomes a clue, a hint at a much bigger idea, the incredible diversity of life. This is it. This is the moment where simple curiosity starts to become real scientific thinking. Now, leading the way on this expedition are two very different but equally important kinds of experts. You've got Dr. Raghu, a scientist who brings the official framework, and then there's Manoram Chacha, a local expert who knows this forest inside and out. And this is so important. You absolutely need both. Dr. Raghu brings the scientific structure. He knows the why behind everything they're seeing. But Manoram Chacha, he has that deep, practical knowledge. He can identify a plant in a second or mimic a bird call perfectly. Real, true understanding? Well, that happens right where those two worlds meet. So as they're walking, they are just surrounded. Everywhere they look, there's something new. Tiny grasses, massive trees, colorful butterflies, and even monkeys leaping around in the canopy. It's this incredible, beautiful, kind of chaotic mix of life all happening at once. You know, all of this amazing variety they're seeing, the different plants, the animals, even those unique bird calls, it actually has a scientific name. And that word is biodiversity. It sounds simple, but it stands for a massive idea. Every single living thing those students saw is part of the biodiversity of that place. It's the official term for all that richness in nature, and it's also a super important way to measure how healthy an ecosystem is. Okay, but that leads to a pretty big problem, doesn't it? With millions upon millions of species on Earth, how on earth do scientists even begin to study it all? How do you create any kind of order from all that beautiful but totally overwhelming chaos? Well, let's bring it home for a second. Imagine your school bag is a complete disaster. Books, pens, snacks, everything all mixed up. What's the very first thing you do? You'd start making piles, right? Books go here, pens go there. Believe it or not, that is exactly what scientists do with nature. This process is called classification. And it's not just about being neat and tidy. It's an incredibly powerful tool that makes it possible to study millions of different things by looking at how they're similar and how they're different. And the cool thing is, the process itself is actually pretty straightforward. First, you just observe. Really look closely at the details. Then, you start looking for what's similar. What are the common patterns? Next up, you spot the differences. What makes each thing unique? And finally, based on all that info, you create your groups. It's a method anyone can learn. All right, so that's the theory. Let's put it into practice. We're going to use the plants the students found on their walk as our real-world example. So, how does it actually work? I mean, what are you looking for to decide if something is a herb, a shrub, or a tree? It really just comes down to a few simple things you can easily see and touch. Take a mango. It's tall, has a thick, hard stem. Boom, it's a tree. A rose? Medium-sized. Its stem is hard but thinner. That's a shrub. Then you've got a tomato plant, which is short and has a soft green stem. And we call that an herb. See? The clues are right there in front of you. And here's a great side-by-side example. You've got hibiscus, which is a shrub with that tougher, woodier stem. And right next to it is tulsi, or holy basil, an herb with a much softer, more tender stem. You can almost feel the difference just by looking at them, can't you? Okay, so let's lock this in. The key difference between a tree and a shrub. Trees get really tall, they have one main thick, woody trunk, and their branches start way up high. Shrubs, on the other hand, they're shorter, and they usually have a bunch of thinner, woody stems that start branching out right from the ground. So, what's the big picture here? The main takeaway? Well, it's that this whole idea of classifying things isn't just for scientists in a forest. This is a fundamental skill for making sense of pretty much anything complex in our world. It really boils down to this simple but super powerful formula. You take careful observation, you add thoughtful classification, and what you get is genuine understanding. It works for biology, it works for that messy school bag we talked about, it even works for organizing files on your computer.
It's all about the fundamental art of seeing patterns. And this is what it looks like in action. The students are back, putting it all together. They're taking everything they saw, everything they observed, and they're starting to classify it, drawing it all out. They are literally turning the chaos of their nature walk into organized knowledge. It's fantastic.
So in the end, it all comes full circle, right back to that little spark of curiosity, that moment of noticing that, hey, not all bird songs sound the same. So here's my question for you. The next time you step outside, what are you going to notice? What patterns will you truly see?
So what if I told you that the two most valuable treasures on Earth are completely invisible, and you're interacting with them right now? Today, we're going to dive into the fundamental elements that make all life possible, the air we breathe and the water we drink. Our journey kicks off with two kids, Bhumi and Surya, who are visiting their grandmother, Aji, and the difference between their city home and this village, it hits them immediately. The air just feels cleaner, the plants look so much greener. This isn't just a feeling, it's a huge clue to the powerful, life-sustaining forces at work here.
Aji tells them that her village is absolutely full of treasures, but not the kind you'd find in a buried chest. No, she's talking about the basic building blocks of life itself. And her first lesson is a really profound one.
I mean, think about that for a second. These elements aren't just nice features of our planet. They are the absolute non-negotiable requirement for our existence. Without them, the story of life on Earth, it would have never even begun. Okay, so let's start with the first treasure, the one that's involved in every single breath you take. Yep, we're talking about air.
Aji taught the kids this simple breathing exercise, and I actually want you to try it with me right now. Ready? Go ahead and take a really deep breath in. Now, hold it for just a second and slowly let it all out. So what happens if you try to hold your breath for longer? You feel that undeniable, kind of urgent signal from your body, right? That's your brain demanding a very specific, critical element from the air to keep every single system running.
Yeah, that urgent feeling? That's your body screaming for oxygen. And think about this. We can survive for weeks without food and days without water, but only a few minutes without air. That's just how essential this first treasure truly is. But what exactly is in this air that we're breathing? Well, it turns out the oxygen we desperately need is actually just a small part of a much larger, totally invisible mixture.
Now this is fascinating. The air we breathe is mostly nitrogen, a full 78% of it. The vital oxygen we need makes up just 21%. And this specific balance is absolutely crucial. See, pure oxygen would be way too reactive, too combustible for life as we know it to exist.
But this invisible mixture isn't just for breathing. Oh no, when air starts to move, it transforms into a powerful force we call wind. And for centuries, humans have been really clever about harnessing its energy. It's such a simple definition, right? Wind is just moving air. But that simple movement, whether it's a gentle breeze that rustles the leaves or a powerful storm, contains an incredible amount of energy. I love this comparison because it's the perfect way to understand the concept. You take a simple paper pinwheel, a firki, and it spins when you blow on it. A massive windmill, it operates on the exact same principle, just scaled up to an industrial level. With just a few simple cuts and folds, a plain piece of paper becomes a tool to catch the wind. As the air pushes against those folded blades, it creates rotation. It's a perfect, totally playful demonstration of physics in action.
Okay, so now let's scale that simple idea way up. These giant blades are engineered to catch the wind with maximum efficiency. And instead of just spinning for fun, that powerful rotation gets harnessed for some very important jobs. And what kind of work are we talking about? Well, for centuries, windmills have been used to grind grain into flour and pump water up from deep underground. And today, massive wind farms use this very same principle to spin turbines and generate clean electricity for our homes. All right, from the air that's all around us, let's now turn to our second great treasure, water. And just like air, it's so common, so everywhere, that we can sometimes forget it's the very solvent of life itself. So let's head back to Aji's garden, where Bhumi and Surya are getting their next lesson. You see, watering plants isn't just a chore, it's a direct demonstration of water's role as a life giver. They're literally transferring this precious resource right into a living system.
But Aji's key lesson isn't just about using water, it's about valuing it. By teaching the kids to make sure every single drop is used purposefully, she's teaching them a powerful idea, that this resource isn't infinite. This simple act in a tiny garden is really a mini version of the global challenge of water conservation.
And that kind of leaves us with a paradox, doesn't it? The two most priceless things on our planet, the air we breathe and the water that makes up our very bodies, are given to us for free. But because they're free, we often treat them as if they have no value at all. The real question isn't if they're treasures, it's whether we'll recognize their true worth before it's too late.
You know that feeling when you're out on a clear night and you just stop and look up? That incredible sense of wonder? That feeling of being connected to something so huge and ancient? Well, that's exactly where our journey is going to start today. So, picture this. Imagine you're Yangdol, or maybe her brother Dorje, living way up in Ladakh. The sky there is almost always crystal clear, with zero light pollution. So every single night, they see a sky just like this, a brilliant canvas absolutely packed with thousands of stars. It just fills you with this incredible sense of awe, right? And that feeling, that's something humans have felt for thousands and thousands of years.
But how do you even begin to make sense of all those little dots of light? Well, for as long as we've been looking up, we've been trying to find some order in that beautiful chaos, connecting the dots to create a sky that's literally full of stories.
I mean, think about it. For our ancestors, the night sky was pretty much just this, a huge, dark blanket sprinkled with bright and dim stars. It's beautiful for sure, but it also seems completely random. But you know what? The human brain is a total pattern-seeking machine.
So, what did we do? We started connecting those dots with imaginary lines, and all of a sudden, that randomness started to look like something familiar, like animals, or objects, or legendary heroes. The stars that make up Orion, the Great Hunter, well, they weren't just random points of light anymore. They became a story.
And that's exactly how we got the whole idea of a constellation. Back then, it just meant one of these cool star patterns, but today, the word has a much more scientific meaning. Now, it refers to one of 88 distinct, officially mapped out regions of the sky. So it's kind of like both an ancient storybook and a modern map, all rolled into one. But here's the thing, these patterns weren't just for telling cool stories around a campfire. For thousands of years, they had a purpose that was absolutely crucial for survival. They basically turned the night sky into an ancient kind of GPS. So was finding these patterns just a bit of fun, a way to pass the time on a long night? Nope, not even close. For our ancestors, this was serious business.
Way before we had GPS on our phones or even a simple magnetic compass, the stars were the map. If you were a sailor out on a huge dark ocean or part of a caravan crossing a mountain pass, well, recognizing the constellations wasn't a hobby. It was a vital survival skill. It was the difference between being hopelessly lost and actually finding your way home.
And eventually, this ancient practice got a modern upgrade. In the early 1900s, the International Astronomical Union basically created an official map of the entire sky, dividing it all up into the 88 distinct constellations that we still use today. They took all those ancient stories and turned them into a universal framework for science.
Okay, so we've seen how humanity mapped out the entire night sky. Now let's use that map to find our own address. It's time to zoom way, way in and take a look at our own cosmic neighborhood.
And this is a really important point. That giant, bright thing that's up in our sky all day, that's a star. It's the exact same kind of object as all those tiny little pinpricks of light we see at night. The only difference is that we're super close to this one. The sun is our very own personal star.
And just how big is our star? Well, try to wrap your head around this. Its diameter is about 100 times bigger than the diameter of our entire planet. Yeah, the only reason it doesn't look that big is because it's about 150 million kilometers away from us.
The sun is the undisputed king of our solar system. It's the gravitational anchor, it's the power plant, it's the whole shebang. Everything else you see here, all 8 planets, their moons, and all those asteroids and comets, they're all held in orbit by the sun's massive gravity. And none of them make their own light. They only shine because they're reflecting the light from our star.
And I just love this description for comets. They aren't some mysterious sign from the heavens. They're basically just visitors from the outer edges of the solar system. They're made of dust, gas, rocks, and ice, and they put on an amazing show when their trip takes them close to the sun. That's when all that icy stuff starts to evaporate and creates that long, brilliant tail we see. All right, so now that we're a little more familiar with our local system, it's time to take one last, giant leap outwards. So, where does our solar system with our special star actually live in the grand scheme of things? If you're ever in a really, really dark place on a clear night, you might see this faint, milky band of light stretching all the way across the sky. That's not a cloud. That's home. That's the Milky Way galaxy. In India, it's called the Akashaganga. What you're seeing is the combined light of billions of other stars viewed from our spot inside of it. And the scale here is just, well, it's mind-boggling. A single galaxy like ours doesn't have millions of stars. It has billions of stars. Our entire solar system, which felt so huge just a minute ago, is just one tiny, tiny speck in this enormous city of stars. And when you look out past our own galaxy, past the billions of other galaxies out there, we arrive at the very edge of what we know. So we're going to end with the biggest question of them all, the one that keeps pushing us to explore the cosmos. So, is there life out there? Are we alone? The honest answer is we don't know. Not yet, anyway. Scientists are searching, they're looking at planets orbiting other stars in our galaxy, but so far, we haven't found any evidence. It's still the great unanswered question, and it reminds us that no matter how much we learn, the universe always has more mysteries waiting for us.